Hi viewers, this is Uncle P and you are on to ECF educational blog. Today we will be looking at the chemistry practicals on quantitative analysis. Quantitative analysis. Please, if you are new in this channel, please always try to follow us, share our video. And if you have any question, you go to the comment section and drop it. Okay? If you are new in this video, follow us, share our video. And if you have any question, you go to this comment section and then drop your question. Still follow the link and have access to our Waec past question and answer as well as JAM, post-UME and all of it. So we're going to be looking at the quantitative analysis of this year's SSCE. I think basically Waec. I'm going to be doing a lot of interpretation to the practical that is forthcoming. Okay, the practical is kind of a rare practical. It has to do with redox, redometry, and oxidometry titration. In my previous video, where we have treated a redox reaction, I would like to refer you to that video once again for you to have an understanding of this aspect of titration. Meanwhile, when we talk about quantitative analysis, what does it mean? It is a measurement of quantities. Measurement of quantities or amounts of acid and base in their solutions. That is what is quantitative analysis. And the only method used to achieve this measurement of this amount of these substances in their solution is by titration. Then what is titration? It is a step-by-step or gradual mixing of one solution that its concentration is already known with that whose concentration is unknown until an equivalent point is achieved, which is accompanied most time by a color change. So this color change is very, very vital in titration because that is when the amount of both solutions, both substances, both active ingredients and substances are present in a mixture, which will be signal that this reaction has gone into completion. And that is what we call the endpoint or equivalent point. So most time when we are doing acid-base titration like that of acid-base titration, we have choice of indicators depending on the type of acid and base. Supposing you are titrating a strong acid and a strong base. Supposing you have a strong acid like HCl, H2SO4 or HNO3, okay, against a strong base like potassium hydroxide or sodium hydroxide. Which indicator is suitable for that titration? Any indicator is suitable because of the nature of the pH. Okay, at the endpoint. So it will be always 7. So any indicator will be suitable. So what if I'm titrating a strong acid and this time the base is weak? Supposing I'm titrating strong acid like HCl, H2SO4, HNO3 with a weak base like Na2CO3, that is sodium triazole 4. What if I'm doing that titration between weak base and strong acid? That means in that titration I'm only restricted to use methyl orange, supposing that the acid is strong and the base is weak. And then if I'm titrating a weak acid, maybe ethanoic acid, when I'm using H2CO3 weak acid and the base is strong base, I will be restricted only to use phenolphthalein. And even if the acid is weak and the base is equally weak, I can also use any indicator for such type of titration. Always know or always take these points, very vital, that in titration of this acid and base, that we call acid-base titration, you must be well acquainted with these two main indicators, your phenolphthalein and your indicator. Always know their colors in their basic and acidic or alkaline medium. What will be the color of methyl orange if you have a few drops of it in the alkaline medium or base? What will be the color? In the moment you can indicate that this substance is a base, if you add 2 drops of this indicator, methyl orange, in the alkali medium, that will be yellow if it is an alkali. So color of methyl orange in alkaline medium is yellow. So what will be the color at the neutral point? Neutral point will be an orange. That is, if it is methyl orange, it will be orange. Kind of light pink. Good, go. Okay, what if you are titrating with phenolphthalein? Phenolphthalein, what will be the color of phenolphthalein when you add few drops of phenolphthalein in a solution of a base or alkali? What will be the color? It will give you pink. Pink. Okay, pink is it. So the color at the neutral point or the equivalent point will be what? Colorless. Okay, but like I said earlier, that we have various types of titration. We have redox titration, that's what we're going to be discussing now. That is under the iodometric titration. Okay, the knowledge of redox is very, very important for this titration. Very, very important. But titration has the same method of procedure for running every titration. Like I'm going to give you a list of 10 things, 10 apparatus, 10 pieces of apparatus that must be available to achieve these reactions in titration experiments. So whenever you are titrating, the following are materials needed. Titration materials or apparatus. First, we're going to be looking at a redox stand with clamp. Redox stand with clamp. And then we're going to be looking at our burettes. Burette of 50 cm capacity. And then we'll be looking at pipettes. And we're going to be looking at our conical flask. And I'll be looking at beaker, clip, funnel, indicator bottle with your choice indicator. We have a white tab or white paper. Okay, these are common indicators, so common materials that is we use in acid-base titration. In acid-base titration, the redox stand will be in this way, standing on your table with your clamp that will hold your burettes in a vertical position. This is a clamp that will hold your burettes in a vertical position with the tab, the last part, the clip, and then the base of the redox stand for standing on the table. So here will be white tab or white paper should be here so that your endpoint can easily be detected sharply. Okay, so now there are some things you must know in this titration. Whenever you set this thing up, you must make sure that your eye level is within the line or what we call the meniscus. Your eye level should be on the meniscus. So assuming here is 0, for example. Okay, this is your table. So other thing that will be on the table for each candidate on this practical will be your beaker containing the two solutions. The two solutions, that is most likely solution A and then solution B. And then your conical flask, I'll choose to keep it here as a cone shape. A conical flask should be here for mixing the two solutions when needed. So actually, your funnel should be here as a delivery tube. Funnel should be here, right here, as a delivery tube. This is a funnel. Okay, so solution of A, which contains the solution of the acid, in most cases, or solution of the oxidizing agent or reducing agent, should in case the reaction is a redox titration. So this is poured right here with the use of this delivery tube or funnel gently until you are able to see the meniscus level. Make sure it is within your eye level. Your eye should be on the meniscus. I repeat, your eye should be on the meniscus. Most time, if this mark is 0, you're going to see that it's going to stand this way. Okay, make sure that the bottom of this, that's the lower meniscus, is on this line. Make sure your eye is directly on it, so you avoid so many kind of error, okay, that will affect your reading. So this is the solution, or the titrant is in here in your burette. And make sure you know that your burette is calibrated. It's 50 cm capacity. It starts from 0, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1. Okay, at this point, this is your initial. This is your initial. So once you have poured this acid into the burette, before you can measure the volume of your solution here, you must put your table as soon as possible. Your table of reading should be drawn this way with your meter rule. This is the model table for Waec. So here we have the series of titrations you're going to do. Titration. Okay, here we're just going to do first, second, and then the third experiment is okay. You don't need to do more than this number. Gone are the days where you run through first, second, and third. No, you don't need that. All that is not necessary now. So you can just do first, second, and third. Make sure that the units are well placed. So the unit for the volume here is in centimeter cube. Always make sure you don't forget the centimeter cube in each of these titles. Okay, now, so make sure before this table you must state the volume. Must state the volume of your pipettes. Most times this pipette come with various sizes. Some can come with 15.0 centimeter cube, some can come with 20, some come with 25, some can even come with 10 centimeter cube. Always record it. But as far as this video is concerned, we're going to be using volume of pipette to be 25.0 centimeter cube as our volume of pipette. Then you have, that is how the table is. And then the first thing here is to draw your final reading, initial, and then volume of A used. Okay, and now that you have poured this solution here, the moment you pour the solution here, record your initial readings immediately. Make sure that both initial reading and final reading must be in 2 decimal places. So here, right here, 0.00. It must be in centimeter cube, since the volume of the base, as the pipette here, is in centimeter cube. Please, very, very important. Very, very what? Important. Now that you have recorded the initial, now what you do is you use another piece of apparatus, which is your pipette, to measure the standard volume of this 25 centimeter cube of this liquid or this solution. So how we use that, we look at how the pipette looks like. This is the pipette. Okay, at the middle of the pipette, there's a swollen part of it. So you have to be very careful. The moment you are dragging this, and the moment the solution is almost here, that means how to reduce the intensity of the way you suck the solution from this piece of apparatus, because you're going to have the mark. There's a mark on this. Once the solution is on that mark, it's expected that you already have the standard volume of your solution here, which you're going to empty into this piece of apparatus. But make sure that you read from the lower meniscus. So the solution, you read this way. Make sure that this is on the lower, not upper. So once the solution is on this line, okay, please, once it is on this line, please take note of these marked places. Please, director, make sure it is seen this way. Please make sure you take a reading from lower meniscus and the lower meniscus from both sides of the piece of apparatus. So you're going to take the contents of what you have here, which is your 25.0 centimeter cube of solution B, empty it here. Once you empty it here, okay, it's already known that this volume of one of the solution is known. Whose volume is known is that of the base. Whose volume is unknown is that of the acid. Okay, if it is acid-base titration, the next thing you do at this point is to get your indicator bottle, your choice of indicator, phenolphthalein or methyl range, and add 2 drops of those indicators and observe the color. Immediately you add, and maybe notice that when you are doing a reaction titrating, that means you're expecting that this color is going to change from what color to what color. That is for acid-base titration using phenolphthalein or methyl range. But as far as this video is concerned, we are looking at iodometry form of titration involving iodine. Please, I would like you to be very careful on this. You are given that the solution A contains 25.4 gram of I2 iodine in 6.0 gram of potassium iodide. That is what A is. Please take notes. And then you also given that B contains 24.82 gram of Na2S2O3.5H2O. That is potassium thiosulfate pentahydrate. So this is your solution of the acid, and this is the solution of the base. So let it be that A is iodide. Let it be that B is the thiosulfates whose water of crystallization just find it. Okay, so what the burette standing here, the content of this burette or the titrant here is I2. And this is thiosulfates. So, what do? We simply titrate it. But I would like us to understand what is this A. Please, the teacher is going to prepare. This video, we're not going to show how we make the standard solution of this. In this video, it's not container, but I'm going to show you what we're going to do and how we prepare this. Okay? So, see, they say that this 25 must be contained. This 25.4 gram of I2 must be prepared in 1000 or 1 dmV of solution. So that means this 25.4 will be weighed, of iodine will be weighed. 6.0 gram of Ki will also be weighed. And 6.0 gram of Ki will be weighed and made to dissolve in 1000 centimeter cube. To be able to make it, since its concentration is known in gram, to know the concentration in gram, we dissolve this 6.0 in 1000. Okay? It dissolves because this is more likely to be polar, and this is non-polar. So this iodine, you're going to weigh 25.4 gram of I2, then dissolve it in the solution containing 6.0 gram of Ki. So what you do is, first, get your standard volumetric flask. Volumetric flask, the other will look like this. Okay, it's 1000, supposing it is. So what I will do first is to measure dissolve 6 gram of Ki here, and then before you make it up, that means it must contain 25 of this before you can make it up to this line. So that means the standard solution of this has been prepared. So what we have in here is both I2 plus I minus. Please take note in this reaction that K is a spectator ion. There's not much thing that K is doing here. So in this is redox, it means that this with this I here, this iodide, this is potassium iodide, we transfer electron to iodine. There will be a flow of electron from I minus to I2. So in that case, I minus will now reduce to I2 here, a balanced equation. Okay, so in this reaction, please, if you make reference to what we did in redox reaction in a previous video, you'll discover that since this I here is -1, and I here is what? Is 0. So it means that I minus here has oxidized to free iodine. This one is free iodine, having lost electron to I2. So when a substance loses an electron, so I minus here in this reaction is just acting as a reducing what? Agent in the reaction. So potassium iodide in this reaction is acting as a reducing agent, having lost electron to iodine in this mixture. So if it loses electron to iodine in this mixture, that means it will then what? Reduce, it will now, oxidize to free what? Iodine. Okay, so what you have here is a mixture of I2 in I minus. But once this happens, that means this I minus has oxidized to free iodine. So the contents, the solution here will be what? Brown. So you'll be seeing a dark brown color of iodine. Most time the color of iodine in most of its solvent is brown. So its color will be most likely be brown. Okay. Then, of course, this is also prepared in the same way. So 24.82 gram of this is weighed in a weighing balance and then make to be dissolved in 1000 centimeter cube of the solution. So that is its concentration, assuming it is known as this case. So in this titration, it is quite different from your normal acid-base titration in that our indicator in most redox titrations, the most indicator we use sometimes in most redox reaction involving a reducing agent like KMnO4. Most times when we use this or this, most times this reducing agents, this oxidizing agents are self-indicator. So in most titration involving these two, the indicators are most likely self, except in iodine, where its indicator is usually what would be in the indicator bottle for this iodometric titration is starch solution. And so now, like I said earlier, the brownish I2 free iodine, which we are able to obtain by mixing iodine with potassium iodide. We already know the concentration, but we don't know which way they are going to go. But first of all, let's try to fill this table before I can give you a question and see how method we use to deal with it. Supposing I've been able to know what we have as the acid, which is the iodine, and then what is the content of the conical flask, which is our sulfates. Okay, now we've been able to pour the acid. I've already known my initial reading. So what I will do is, I will not add any indicator yet. I have to titrate. It's not like your acid-base where after emptying the content of the pipette here, you add 2 drops, you observe color. No, this titration, you have to titrate 2 times. The first titration will be like, you start titrating. So you can see, you can know there will be a calculated amount of iodine that will go in here. So the moment iodine is going in here, the color of this will change. You have to be very, very observant in this reaction. The color of iodine the presence of iodine going in here will change the color of this beaker, the color of the mixture here, to what? To brown. So you titrate until the brown fade. Once the brown, so that there won't be much complex iodine in it. As the brown fade, maybe it is trying to fade and it's trying to change to something yellow. Please, you have to check when you add few drops, it becomes brownish. And then you'll be adding gradually until you obtain yellow. Once you see yellow, you stop titrating. And then go to your indicator bottle containing starch solution. Add few drops of starch solution. The moment you add few drops of starch solution, this particular content that was initially not brown now, having added some few of this. So when we have more calculated amount of iodine in this mixture with the sulfate, it's gradually going to fade to yellow. So when you add few drops of iodine, the color will now change to blue, black, or intense blue, or dark blue. Always know that iodine form complexes with starch. So the presence of iodine has been confirmed, has been indicated in this solution. That's why it turns the word blue-black. So after adding that starch solution on this mixture, and you indicate blue-black, then you now start titrating the second time. So you have to be very observant when this reaction will come into completion. When the color will change, there will be a color change where the blue-black changes to colorless. There will be a change in this color from blue-black to colorless. At that point, you have to stop titrating. That means there has been an equivalent point achieved. So what I will have that this free iodine that has give electron to iodine to form free iodine, this iodide give electron to iodine to form free iodide will actually react with thiosulfates to form this plus iodide. Actually, in this reaction, iodine has reduced from iodine to iodide. That is what happens when these two are mixed together. So that the color has changed from blue-black to colors means that there is no iodine in the mixture again. So the all iodine have been converted to iodide, having allowed to mix with what? Thiosulfates. That is why there is a change in the intense blue or blue-black color, indicating the presence of iodine in the mixture initially. So in this case, why this equation is very, very important. Sometimes the examiner will try to give the equation because I know that this equation is what gives students more problems they encounter in most volumetric analysis. But as it is, the equation, sometimes the examiner will give this equation, but you will also know they have to do something here. How many moles of iodine is actually reacting in this equation? It's just one against 2. So the ratio of this reacting with this is what? Is 1:2 of this. Okay, it is very, very necessary for this reaction. So let me assume that the moment you titrate the first time, the moment you allow this by opening the clip to allow some amount of this to go in here, the color of this thiosulfate will change to brown. You have to titrate until it becomes yellow before you stop titrating. By that, the solution here is going down. So if you go down, once you change from brown to yellow, you stop titrating, add a few drops of starch indicator, observe the color, which is blue-black, titrate the second time until you ensure that the blue-black turns to colorless. That time you have to stop titrating. Any point it turns to colorless is your endpoint. Okay, that endpoint is written as final reading. So let me assume that the final reading here is 12, or maybe is 13.20. That is what I'm assuming. Okay, and then you have to ensure that you always subtract your final from initial. So what you have is 13.20. Supposing that is what you do first. Sometimes we usually call this first titration rough. Any titration, any experiment, an experimenter must first of all do some kind of rough titration so that the experimenter will tend to have an idea. So all candidates is expected to run a titration which is going to be trial titration before your main experiment. You can try it and without even recording it. You are not at liberty not to do that. You can do that without recording anything and maybe do it and discard it and then do fresh titration. That will give you an idea of the range of the endpoints. Okay, so but let me assume that this is going to be my rough titration as the first titration. So I will be more careful doing 2 more. So I'm going to start the whole process all over again as far as this 2 is concerned. So I'm going to refill the jets again and take my initial. Let me assume I'm taking an initial from 0. Make sure it is in 2 decimal places. It's very, very important. Okay, I do the same thing I did in the first titration again by first pipetting. I already know the volume of the pipettes and empty it in this conical flask. I will not add indicator immediately. I have to titrate until I have some calculated amount of iodine in the mixture before I will stop and add few drops of starch indicator solution to it. I will observe the color is going to be intense blue or blue-black. Then I will start the second titration. When the blue-black changes to colorless, I'll stop. And maybe at this time, stop at 12.70. Okay? So here will be what? 12.70. Okay. So now, I have the last titration, which will be, I'll have to fill in again, put down my initial reading, and then maybe at this point, I will be able to get final at 12.60. Here we got 12.60. So this is what the student were able to obtain from this experiment involving iodine versus this. But remember that iodine is in potassium iodide. Potassium iodide will help due to common ion effect to dissolve iodine, since it is very polar. May not be that easy for it to dissolve in water, since water is polar while itself is a non-polar. This is what is obtained from this table of reading. I shall tell you what to do as far as this table is concerned. As far as this table is concerned, there's what we call issue of concordance values. Concordance of values that are consistent. Value in chemistry is very important to know that. As far as table of reading in titration is important, please, you should know that in this titration you cannot use 13.20 because it doesn't conform with others in terms of plus or minus 0.20 centimeter cube as per the differences. What I mean is, if you use your calculator, press 13.20 minus this, check if the difference will be within this. I don't think it's within this. But if you use 12, if you look at 12.70 minus 12.60, difference will be within this. Difference should be 0.1, I think. So that means only out of the 3 experiments I was able to carry out here, only 2 were concordant. It's very okay, very correct. You can even do a titration whereby 3 of them were concordant. You use the 3 as an average titer and get your average volume of acid used by the 3 experiments carried out. But in this case, only 2 conform. Only 2 out of the 3 were concordant. So I'm going to use 2 and get my average by dividing by 2. Okay, so most times we see questions this way. An examiner will say A. Okay, now, so we have the table obtained for this reaction. We already have the equation, balance. I think the examiner will always give you the equation of this sort. So you don't have to bother yourself. So this is A containing the molarity is known. The concentration is known in mole per dm cube. So actually that is why A is poured into the burette. So its standard solution is known. Its concentration is known. Okay, what is standard solution? The concentration whose concentration is known. A solution whose concentration is known accurately is standard solution. So we're going to use this solution that is standardized here to try to know if we can use it to get this concentration whose concentration is not known. So this is standardization of this one using a standardized solution of Ki, sort of iodine. So most times an examiner may maybe give you this one as standardized and this one unstandardized. So what you will do, that means this one is actually going to go in here. This one is actually going to be here. So that means the method of now mixing the both until the reaction is complete is what we refer to as titration. So other things will be put A into the burette. We have done that. You have put this into the burette and then titrate it against 25 centimeter cube of solution B. This time using starch indicator solution or solution of starch solution. Starch indicator solution, not paper. Okay. So that is it, but they will have to explain to us how we're going to add this indicator, starch indicator, whether we're going to add it immediately when we pipetted the solution B, or whether you're going to titrate without indicator. After some time, you now add indicator so that some calculated amount of iodine must have been in the mixture for it to actually form complexes with a starch to give you that dark blue or blue-black before you start a second titration, which will actually color changes to color. Let's explain that at that time that the whole iodine in the mixture has been changed to iodide. So since there is no iodine in the mixture, Okay, that means that that complex 6 iodine formed with starch will disappear since there is no iodine, since all the iodine has reduced to iodine ion. So that is what happens to the mixture that made it to change to colorless. An interesting practical if you carry that out. I believe by this analysis I'm giving to you concerning this titration will go down well with you. All other thing remains the same as far as this practical is concerned. The same way you solve in acid-base titration is the same way. The only thing here that in this titration, you are not using your usual indicator like phenolphthalein, your methyl, your methyl, your screen this or that. You are going to use a different thing entirely. But the process still remains the same. So when we do that, the most important thing, since concentration of A in this reaction, in this question is known, what you now see is that the B part of the question is what we are interested in. This is the A part of the question with the experiment. So the B part of it will be, from your results. From your results and information provided above, calculates. No more to calculate count of A again because it's already known. So it will be calculates concentration of B in mole per dm³. Okay? You will see another question like concentration of B in gram per dm³. Okay, let's do this aspect of this calculation, having on this. So what do I do? Please remember, I'll still go back to the table again to still state our average titer. Very important. Average titer from this, we're not going to use this. Okay, we say average titer is 12.70 plus 12.60 all divided by 2. I think that gives us 12.65 centimeter cube. This is our volume of the acid. Okay, so we use values that are consistent or values that are what? Concordance. Okay, then that has answered question number A. Okay, and question number B is going to be from the information I have now, and then information you provided, this is the information provided. Let's see how we're going to calculate conc of B in mole per dm³. Conc of B in mole per dm³. Please, from the reaction, I will state this equation again. I2 plus 2S2O4 2 minus O4 2 minus plus 2I minus. We don't have any need for this one. What we have is this one. So here we have 2. So already we now have that our CA, which is I2, is already giving us 0.100. Our VA, that's our titer value from the table, those concordant values where we have 12.65, and our NA is just iodine. It's just one. Okay, this side we have our CB is unknown, the way we're looking for. Our VB is the stated volume of the base, which is 25.0. Our NAB is 2. Okay, what do we do now? So we use the formula method using CAVA all over CB VB equals to NA all over NB from our equation, from the balance equation here. It will be given most time. So what do we do? We substitute now. We have CA 0.100 multiplied by 12.65 over CB times VB, which is already given as 25.0 is equals to NA1. This is 2. What do we cross multiply? And then we have 0.100 times 12.65 times 2 give me 2.53 is equals to 1 times 25 times CB will give me 25.0 CB. Okay? So what we do, we divide both by 25.0. Here 25.0. Here we have 25.0. This cancel this. So here we have CB now is equals to this divided by 25. Gives me CB is 0.101. Please, the unit is very important. Mole per DMQ. That's my CB. That's my CB. As simple as that. You can pause the video and check where you have problem. Please, you can indicate on your comment section, please. That's very simple. But another way we can still solve the problem. Another way we can still solve this. You're not using formula method. Should in case maybe you forget the formula to solve this problem, you can use our normal conventional method of solving. Okay, let me use conventional method and see which you prefer. Suppose I want to solve my alternative method of solving this molarity alternative method, or I can call it formula method of solving. So what I'll do now is okay, I'll have to find the amount of A in its volume, which is find amount by saying molar concentration or molar conc multiplied by volume over 1000. That's all I need to do here. The molar concentration of A is given as well. Look at it here, 0.100 times volume of A is 12.65. Remember where we get this, over 1000. Okay. So we have 0.001265 mole of A. So now from the equation, I'm having 1 mole of I2 and actually reacted with 2 moles of S2O3 2 minus. Okay, therefore if 0.001265 will now react with what? X. So X now is 0.001265 times 2 moles over 1. X will be mole of B. X will be mole of B. Let's see. So we multiply. We have this already. 0.00253 mole of B. Okay. Therefore now, molar concentration or conc of B mole per DMQ. Molar concentration now. Molar concentration is equals to amount times 1000 over volume. So amount of B is 0.00253 times 1000 over 25.0. What is our final answer? That should be, that's giving me what? 0.101 mole per DMQ. This is exactly what you get in your formula method. So whichever way you choose to use to solve the problem, that is how to find our molarity or molar concentration of B. That is this aspect, BI. So this alternative method of solving question what? BI from this problem. Okay. If you say we're going to look at how to find, having done this time is very easy for us to calculate concentration of B in gram per DMQ. You can pause the video and make sure you follow every step in this problem. So I'm going to do this B part of it, that is BII. Okay, now for this now, that is BII. How do we do this? First of all, go back to the question and see what is B. So B is unknown concentration. That means what is unknown here is the mass concentration. So mass conc of B in gram per DMQ is yet to be known. Okay? So why we know that molar conc of B is 0.101, and then I can get molar mass now. Molar mass of B, which is Na2S2O3 dot 5H2O. Okay, the mass of one atom of sodium is 23 times 2 plus 32 times 2 plus 16 times 3. Okay, then we have this as 46 plus 64 plus 48. Okay, let's see the addition of this immediately. That gave me 158. Remember that 1 mole of water is 18. 18 times 5. 18 times 5 molecules of water there gives me 90. So I'm adding with 90 of water there. Okay, so all together I'll be having a 158. That's giving me 248. So that's the molar mass of B. So therefore, molar concentration, molar con is equals to mass conc over molar mass. So let me substitute now. What is my molar conc? Molar conc is 0.101 is equals to mass conc is unknown. Mass conc over molar mass, which is 248. I can cross multiply now. I have that my mass conc is equals to 0.101 times 248. Okay, actually giving me 25.048. I can actually want to keep my answer in 3 significant figures. I think that will be just 25.0. Okay, so I can keep the answer like this. That's 25.0 gram per dm. Since they say keep concentration of B in gram per dm, which is the mass conc. That is what we do to do this. But I'm going to see this question in another perspective. I'm going to give you the question in another perspective. I would like you to pause the video and try and see if you can solve it, following what we did previously. Hi viewers, let's look at this question another way. Examiner will want to put the question out there to you. I would like to, we are still using the same concentration, the same iodometric titration, but this time I'm going to see how we interchange the question. What if I say A is a solution containing 25.4 gram of I2 in Ki per dmq of solution. And then B is a solution of 24.82 gram of Na2S2O3.5H2O per dmq. Okay. The other thing you will see, okay, let me make it X or N. Okay, let me call it X. Okay. Other things you will see again, say put A into the burette, titrate it against 25 cm³ of B using a starch indicator solution, and then do the titration 2 or more times to see if you can achieve consistent titers. These are the things you need to do, but the most important thing in this video now is to know how to calculate the problems that follow the practical. Okay, what we do now is this is information given. Okay, let's say that the average titer for this, everything being equal, average titer from our table is 12.65 cm³. Okay, viewers. So now they say from BI, then we are asked to calculate concentration of A in mole per dm³, and then II concentration of B in mole per dm³. III molar mass of B in gram per mole, IV value of X in B. What do we do? In this problem, already we are using the same table, but this time we're using the average title of the first formula. You can pause the video and try and see if you can solve this. Okay, so we start. What do we write? We start from BI. How do you find concentration of A since A and B, their molarity is not given? So to find concentration of A, I will use this relation immediately, which is, I will say that molar concentration, that is concentration in mole per dm³, is equals to mass concentration, mass conc over what? Molar mass. Remember, some information will be given, which is they will give you that the I here, molar mass of I is 127, S is 32, O is 16, H is 1. Very, very vital for this. So that with this now, since A is I2, so I can find the molar conc now. Molar conc is equals to mass concentration here is giving us 24.4, or rather 25.4 over, right, from this A containing, that's the mass concentration of A, the molar mass of A, from the atomic mass of iodine. Iodine molecule will be 2 times of this, which is 254. Let's be sure of that. If one atom of iodine is 127, so molecule will be 254. We are correct. 254. So how do we get the molar conc of iodine now? So we say 25.4 divided by 254. That is 0.1. That's actually what you get in the calculator. Please make sure you keep your answer in 3 significant figures. So I have to add 2 extra zeros to it. Write your mole per what? dm³. That is your concentration of acid. You can call this molar conc, can also be called what? Ca. Okay. That is what it is. Then for BII, how do we calculate concentration of B? This time I'm going to state the equation for the reaction, but I'm going to use ionic. So ionically it will be between this and this. This is the spectator. So that will be I2 plus S2O3, 2 minus, what goes there is what? S4O6, 2 minus. So here will be balance plus what? 2I minus. So from the equation, the mole ratio, I say from the equation, mole ratio of A, this is going to be A, is going to be A to B is 1:2. So using CAVL upon CBVB equals to NA upon NB. Okay, our CA is known as 0.100 times 12.65 upon CB times 25.0 equals to 1/2. We cross multiply. So what we have now is 0.1 times 12.65 times 2 is 2.53. 2.53 is equals to 25.0 CB. So divide all by 2 points, 25.0 over 25.0. So this cancels this. So our CB now is this divided by 25. So what we have is 0.101 mole per dm3. This is our CV. Okay, this is exactly what we did in the first question. So that's answered question B. Let's pause the video. Okay, then let's go to BII immediately. BII. BII, which is the molar mass. So we are looking for molar mass of B is unknown, but we know the molar concentration. Molar concentration of B is, we have it as 0.101, okay? And then we are going to find the molar mass, so we know molar conc. So we know the mass conc already from the question how B is prepared. Mass conc of B is giving us 24.82. So what are we looking for? Stating the obvious, which is this relation that molar concentration is equals to mass concentration upon molar mass. Molar mass. So let's do our right substitution here. Molar concentration is 0.101 is equals to mass concentration is 24.82 over molar mass. So let's find the molar mass now. You say that molar mass is equals to 24.82 over 0.101. That gives 245.74 blah blah blah, but I can correct it to the nearest number. We have 246. Unit is gram per what? Mole. That's the molar mass of the base obtained. So that is on that note. Pause the video and make sure you follow it step by step. If you have any question, you go to the comment section and drop your question to be attended to. So we are going to look at the last question there, the value of this x. What is this x? What is this x? That is the next question we're going to look at. Okay, so now the value of x, that is BIV now. Value of x. Value of x in Na2S2O3 dot XH2O. Let's take it. Let's say Na2S2O3 dot XH2O. Let everything be equal to the relative molecular mass, which we just find out to be 246. 246. That's the molar mass. That's the former question just on III. Okay, let's get the atomic mass of all the elements here. This man is 23 times 2 plus 32 times 2. That's mass of sulfur is 32. So how many atoms are here? 2 plus 16 times 3 plus water is 2 plus 16, which is 18x. Everything is equals to 246. Okay? So this give me 46 plus 64 plus 48 plus 18x equals to 246. Okay? So all together 46 plus 84 plus 48 already give me 158 plus 18x equals to 246. Okay, let's make x the subject of formula here. Have 18x is equals to 246. This going over here, go minus 158. 18x is, that is 88. So we divide all by 18, or you say x alone is 88 over 18. X is, that gives me 4.88 till infinity. But you know that in this case, value of x must actually be a whole number. So X here is actually what? 5. So if you look at it from what is given in the first equation, here was what? 5. It means that this is sodium thiosulfate pentahydrate according to the value of X. Sometimes in this question, you see A is a solution containing half of this. Let's see what half of this is all about. Let's say half of that, which is actually 25.4 divided by 4. Actually, it's giving me 6.35 gram. But this time of I2, I'm not going to put this way. I'm going to say in this per 250 centimeter cube. Okay, in this case, what if the question is changed this way, not as former? What do you do in that regard? Before you can find the molarity of this, make sure you get the mass conc of this, not the reacting mass. The mass concentration must be the amount of this solute in 1000. So that means if actually that this is in 250, that means I have to find what will be in 1000. So if actually that 6.35 is contained in 250, please have to do 1000 will contain what? X. So what will be actually in 1000 is going to be your mass concentration, not this. So that is when, if you do that, you're going to have X is 6.35 times 1000 over volume 250. X will actually still give you that 25.4, I think. 25.4. Let's us be sure of that. So this is going to multiply by 1000. So let's see. 6.35 times 1000 divided by 250. Oh, correct. 25.4. So this is our mass concentration. So if you want to go to molar concentration, that will be this over 254. That is the molar mass of I2. That will give me 0.100 mole per GMQ. So that is how to do this, how to get this, supposing the question goes this way. So now I've solved BI, supposing we have this as the reacting mass. So how I will get this, we now be using formula method, CAVA, or I can use the other method, which is the conventional method, maybe statement method. You can use to actually get the molarity of B, and then do your relationship between mass conc, molar conc, and molar mass. You actually find this, and then you'll be able to find the value of X. Thank you for watching this video. We appreciate. So at this juncture, I think we come to the end of this series of practical chemistry on iodometric, redometric, and oxidometric titration. Thank you very much, viewers.